Topic of the day is MHD, and right now I think Daniel needs no introduction.
Thanks, everyone. All right, so you've been wondering for the whole 2 weeks. You've had the burning question in your mind. What about magnetic fields? What about magnetic fields? What about magnetic fields? If you ever have to chair a colloquium, it's the question you can always ask at the end of a talk. What about magnetic fields? Did you consider magnetic fields? So here we are. So we are going to consider magnetic fields. How should we do this? You remember these? What are they? They are Maxwell's equations. And so they are the equations of the electromagnetic field. They're a little bit weird because they're not exactly symmetric. So you have electric charges, but you don't have magnetic charges. Actually, that's the big issue we're going to come to is exactly this. The fact that you don't have north poles existing by themselves is what this equation tells you. Rho C here is the charge density. It's the number density of electrons minus the charge on the ions times the number density of ions. Okay, so the question is, well, what we don't really have in astronomy is static electric charges. And so we want to rewrite these equations in a way that gives us something to do with the B field, but we don't really care about the static charge. We'll come to why that is in a minute. So there's a good way and a bad way of deriving MHD. If you look at my YouTube channel, you'll find the bad way. So let's just discuss the bad way briefly. So the bad way, I mean, it's not bad, it's kind of fun, but it's just like plucking things from the sky. You don't really know where it comes from. You say, let's transform to the co-moving frame. So we say E dash is E plus B cross B. Where does that come from? Well, it's like Lorentz transformation, some kind of non-relativistic limit of a Lorentz transformation. Okay, you have to be very careful already because Maxwell's equations has two non-relativistic limits. So you can take V much, much less than C, but you can also take E much, much less than CB, or you can take B, C much, much less than E. So there's an electric limit, a magnetic limit. You're already in trouble at this point because you're not sure what you're doing. But with due care, you can say, okay, there's a transformation to a co-moving frame. So in the co-moving frame, you take a generalized Ohm's law. What is that? I say, well, magnetic current in the co-moving frame is some resistivity times the electric field in the co-moving frame, which, for example, could be 0 if it's a perfect conductor. Okay, so that's what we call ideal MHD, means no, sorry, the other way around. That's not right. E equals 0, so E dash is J on, so perfect conductor is sigma goes to infinity, so equals 0, so E dash is 0, not J. Yep, so we'd say, well, that's a perfect conductor, and then you just go back to your Maxwell's equations, you say, well, what is this E? Then you say dB dt, and it doesn't matter, B is the same in the co-moving, non-co-moving frame, is minus the curl of E. E is E dash minus V cross B, so that gives you a plus curl of V cross B. Okay, so in 2 seconds, we've derived the induction equation of MHD really badly. All right, happy with that? Probably seen it before, roughly. Let's go a little more slowly and say what you should do, because why do I want to do this? Because I want you to learn where MHD comes from as well, and it does come from Maxwell's equations, but it also comes from plasma physics. So let's do it the good way. Okay, so what's the good way? So what you really have in nature is ions and electrons. We're doing fluid dynamics. So let's do fluid dynamics. So this is your like favorite equations of fluid dynamics. Electrons, electrons. Electron pressure, identity matrix. I don't know how you want to draw these. Phil was having trouble with his, how do you want to draw a tensor? So it's this is a weird object in hydro. This is what you call dyadic notation. So it's really a tensor, right? It's an outer product of two vectors. So it's kind of funny writing divergence of a thing which is actually a tensor. So what you really should do is use tensor notation, but we kind of only have one thing in the fluid equation, so it seems like a bit of a waste. But you should just be aware of this. So this is what you call dyad notation, also dyadic notation. It's kind of nice because it looks like vectors, but of course this is not a vector, this is a tensor. Are you just totally confused now? Yeah. Just think about the rank, right? So if you think about there's a vector here, so divergence of something, the divergence of the whole thing has to give us a vector and has to be added to a vector. So in other words, this is like in sort of matrix form, it's a 3x3 matrix, right? It's the 3x3 identity matrix.
Both those things in the parentheses?
VE, VE.
No, because you have a grad.
That's a density. That's a dot product. This is velocity.
Okay.
This is the equation of fluid dynamics, regular equation. The only thing I've done is tagged it with an E for electrons. Okay, what's on the right-hand side? Well, electrons, they feel electric fields and magnetic fields. So we've got an E plus V cross B. And what else? Well, we'll come to the coupling in a minute. So that's just your regular fluid equations, but with an extra force from the fact that I'm charged. Okay, no hokey business here. So same thing with the ions. Divergence of rho ion, V ion, pressure on the ions, identity matrix equals, well, they're positively charged, so it's plus. Now, right, just to keep things simple, I'm going to assume that they're once positively charged. That gives us a plus ENE. It's very easy to write a Z in there as well and make it, could be any charge. But let's say we've got a species of negatively charged electrons, a species of once positively charged ions. In general, what else would you have in an astrophysical gas? What other species might you have? Well, you could have neutrals. Yeah, so in general, we should do a 3-fluid treatment, which will give us one extra thing. Okay, now the other thing that happens is we've got some coupling between the two fluids. Okay, we'll call this, we're just on it's just some constant at the moment. Well, it's not really constant either, it's just some coefficient. And we're going to have some momentum exchange between the electrons and the ions. So ions minus electrons. Okay, so this is plasma physics. Basically, we've got ions, electrons, neutrals. We could have like many species in general. This is what you call a multi-fluid set of equations. So why is this kind of annoying? Because, well, you can do this kind of thing. So you can simulate electrons, you can simulate ions, but a lot of the time these coupling terms are going to be very strong, as in they're going to be very large, which is what you call a stiff set of equations. So very large terms on the right-hand side is kind of bad. It's actually the same set of equations if you do like dust and gas. You would tag this as dust, this as gas. Obviously, no, it's even simpler with dust and gas. You have no like electric forces unless the dust is charged, in which case then you have charged dust and uncharged dust and things get real messy. Dust has no pressure either, so that's also a difference, but it's the same procedure in general. Okay, so what do we do if the right-hand side terms are large? What's a sensible thing to do? That's a minus, that's a plus. How can I cancel them? Add them together. Yeah. So if we just add these together, what are we going to get? We're going Well, so I'm going to define, let's define a couple of things that are going to be helpful. So we're going to define a velocity, which is the center of mass velocity, rho ion v ion, over rho electron plus rho ion, which I'm going to call rho. This is just going to call rho. Yep, so rho is rho ion plus rho electron. In practice, of course, ions weigh much more than electrons, so you don't really care about the electron mass. And likewise, this V is approximately also V ion for the same reason. But we're not going to go there just yet. We don't have to go there right now. We will go there eventually. But this V at the moment, and you can imagine doing it with many more species, is just the barycentric velocity of the fluid mixture. And you could have n species and you would just continue the sum. Okay with this? Okay, so let's add the first term. What do I get? d dt rho VE plus rho VI equals rho times V. Straightforward. Yep. Plus divergence of. Okay, now what I'm going to do is I'm going to write down also some drift velocities. So the drift velocities are the difference between the ion speed and the barycentric speed. The electron drift velocity is the electron speed minus the barycentric speed. Okay, but the first term in all this, so if I have V electron plus V ion, then V ion is just going to be equal to V plus the drift speed. Yeah. And so V electron is going to be equal to V. We've got the minus sign correct. Yes, looks all right. Add things. Okay, happy with that? So the leading order term here is going to be a VV, VV. Yeah, so I get a rho E plus rho I, VV, which is just a rho times VV. Happy? Okay, so where are we going with this? This is going to be basically, well, so let's do a pressure, which is ion pressure plus the electron pressure. This is just going to be basically the exact same thing, just with total quantities instead of individual quantities. This term goes to 0. What about this term? So this term goes away, the coupling term. What happens to this term? Well, this is an ENE. Okay, so the ENE E term goes away. This is a V electron, this is a V ion. So it's a V ion minus V electron cross B.
Do you ignore the W terms?
Not yet. They're here. Div dot. So there's a term here, WI plus rho WE, basically. Yep, so they're here. But I'm about to ignore them, which is why they're off here. Yeah. So you can say, well, if the drift terms are small and these are doubly small, yep, so we can neglect this term. And as long as the fluids are well coupled, which is kind of the reason I'm doing this approximation in the first place. In other words, as long as these terms are pretty big, then that's a pretty good approximation. Now, what's this term in the middle? Let's define something we're going to call J. What's J? Well, ENE, V ion minus V electron. Yeah, as in it's the currents are basic electrons and ions moving differently. So what do I get here? So this gives me J cross B. And I didn't even go through this bit of the MHD equations derivation, but we've got a force on the right-hand side which arrives nicely. If I include a Z here, I would just redefine, I would just end up basically with a, oh, you have to put the NE inside, but the Z, you would just redefine the current and actually the same thing drops out. If you have 12 fluids of different charges, the same force appears on the right hand side. It's always J cross B. Everyone happy? All right, and we've neglected a sort of second order term to do with assuming that the drift speeds are small. So drift speeds are not small, we're in lots of trouble anyway. And ions and electrons are pretty well coupled, like they're, well, basically electrons, because they're quite low mass, they end up they respond very quickly to the magnetic field, so they couple very strongly to the bulk fluid or to the other charged species. Okay, but we're missing one piece of information, so we added them, but we've got two equations down to one equation, so we must have lost some information. So where's our extra information gone? What else can we do apart from add them? Minus, I actually don't want to minus them, but I could just use one of the equations. So let's just use the electron momentum equation. And I'm going to write it in Lagrangian form. So this is just the regular equations of fluid dynamics, right? So I'm going to assume that you can write it both in Eulerian and Lagrangian form. But in Lagrangian form, this would give you a dVe dt. You have to be a bit careful by what you mean by dVe. So this is a, so ddt here is a ddt plus v electron dot grad. Yeah, so it's a ddt with respect to v electron. But this is going to give me like regular fluid equations, but with electrons here. Yeah, that's what that left term can be translated into. So I can rewrite the left-hand side as those two terms. Happy with that? And then what have I got left? So all the other terms are still there. So minus E and E, E plus V electron cross B. What else? Minus this collisional term KEI VI minus V electron. That's going to for sure go off the video. All right. So what's the point of this? Well, so for MHD, you want to make a very particular assumption. And the assumption is that you can neglect the inertia in the electrons. So what's the inertia? Well, the inertia is like the acceleration. So the sort of time it takes for the accelerations to be, for the electrons to be accelerated. In other words, we say that this whole thing is equal to 0. Now, one thing that's real confusing if you talk to plasma physics is that not neglecting the electron inertia is something that in plasma physics is called ambipolar diffusion. In astrophysics, ambipolar diffusion is a drift between neutrals and the rest of the magnetic field. So it does get a bit confusing, but let's just call this neglecting electron inertia. It does have different names in different fields. Okay, so what does this do for us? Well, so now we can just got an expression that we can rearrange. And what's an expression for? It's an expression for the electric field. Is actually the thing we're missing. I just rubbed them out. But the thing we were missing in Maxwell's equations is we have dV dt equals minus, I think, the curl of E. So the only thing we need to like get our equation of motion or our equation for the evolution of the magnetic field is an expression for E. Okay, so we've got our fluid equation right here. It's all done basically. So this is, well, in Lagrangian form, this is dV dt equals minus grad P on rho minus J cross B on rho. We derived that already. So we're only missing one equation, which is the bit that tells us how the magnetic field evolves. Okay, so now we have an expression for this from our electron equation, which is exactly this. So it's a minus grad P E over rho E sorry, over E NE. So NE here is like rho E over the mass of electron. What else is in here? We get a minus V electron cross B. Plus this collisional term Ke Me over E, the ion minus the electron. Okay? Happy with that? So all we've done is we've used our electron momentum equation to get an expression for E. Now we can simplify this a little bit further. Now remember that J, how do we define J? So we've got J equals ENE VI minus V electron. So I can rewrite V electron as J over ENE plus V ion. Okay. You're looking at me blankly. Yep, so J over ENE gives me VI minus V electron. Yep. Okay, so let's go even further. So this gives us E equals minus grad PE over E and E. This one gives me J cross B over E and E. Then what have I got? Minus the ion cross E. Oh, sorry, cross B. And I'm just going to collect, well, this thing also looks like a J, right? So VI minus V electron. So I'm going to call this thing a J over, please tell me I'm on the video. I'll call it just sigma. Sigma is defined as all of the stuff that was in front of this. So collisional term, something to do with how ions and electrons exchange momentum. Okay. Well, that's starting to look pretty good. If I say that that's approximately V, this is my generalized Ohm's law, not dodgy. I haven't made any frame transformations or weird stuff. So that's your generalized Ohm's law. And if we go back to our Maxwell equations, so therefore, dB dt is minus the curl of E, which is the curl of B cross B. But what else have we got? We can erase this one now. What else is in there? You're all very silent this morning. It's like overwhelmed by MHD. So that's neglecting a lot of terms already. So that's just this term, B cross B. What else have I got? Well, I've got, I'll do a plus, the curl of J over sigma minus J cross B over E and E. What's this term? Well, it's something to do with the drift between electrons and ions. That's it, I've only got one term left, which is the plus grad PE on rho E. Sorry, E and E. Okay, so what's this? Well, so this is what you call ideal MHD. So if you assume that the electrons and ions are perfectly coupled, for example, the collisional term is is infinite. So sigma is 1 over the collisional term here. So if this collisional term is infinity, then this term will go to 0 because sigma, sigma is the conductivity. So the electrical conductivity. And it's to do with, well, you can see where it comes from actually. It comes from understanding how electrons and ions collide. So if you wanted to like work out the physical value of the resistivity, for example, in a simulation, you just have to figure out what the actual momentum exchange between. So that's just a literal cross section of interaction. It's like the size of the ions, size of the electrons. So you can just get physical terms by understanding what this collisional term is. Okay, what's this term? This J cross B on E and E. So this thing is called the Hall effect. Does not destroy the magnetic field. What it does is takes the magnetic field and puts it in a different direction. It's not dissipative. So if you do B dot this, it basically tells you what the energy dissipation is. So B dot, this thing will give you something which is positive definite, which gives you heat. In other words, this converts magnetic field into heat. This thing is the Hall effect. It just does something weird. Takes rotating things that weren't rotating and starts them rotating backwards. Okay, it's the drift between the electrons and the ions. What is this thing? It's just a term. It doesn't have anything to do with B in it. It's a term which, if I had zero magnetic field, I would get some non-zero term on the right-hand side, and it would make magnetic fields for me. So this is called the Biermann battery. Cosmologists use it sometimes to try to make magnetic fields in the universe where there weren't any. It's a numerical disaster. It's a numerical disaster because we've like kind of brought in like one term from here, but neglected the other one. And of course, in the regular fluid equations, what you would have is an energy equation that goes with it. There's PDV work that sort of matches this term. And we haven't got any like PDV work happening in the electrons. So this totally violates all your rules about like entropy should increase. It can do whatever the hell it wants. And so there's various papers. If you search for Biermann battery on ADS, the sort of terms you come up with in the titles is like the Biermann catastrophe and numerical Magneto-Hydrodynamics. Basically, because if you start just chucking a random term in here with no extra control on the entropy, you're going to get disasters happen. So people try to do things like smooth the gradients, try to make it not very big, this kind of business, but just basically don't do this ever. Or if you're going to do it, go back to thinking about plasma physics. Okay, so there's one extra term that we also neglected, but if we did do the neutrals as well, then you end up with an extra term here, which is which we call ambipolar diffusion. I'm going to call that eta A. So you would end up with an extra drift term if you did the 3 fluid thing, which we didn't do, which would give you an effect due to the neutral ion drift. Okay, so what's good about this is we've done no hokey business, no frame transformation. We just use ions, electrons. We added them together. We've got regular fluid equations. What's changed about the regular fluid equations? Well, nothing. The only thing we've changed is we've got, now what does this V represent now? It's the center of mass. Yep. So we're following the barycenter of the mixture. Yep. So we're not following ions. We're not following electrons. The barycenter is going to be very close to the ions. We've kind of made that assumption already because we dropped those second order terms. So it's going to be pretty closely tracking what the ions are doing. But the only thing we've got different, and this was true no matter how many fluids we got, we just depends on our definition of J, that's going to be the extra force. So we basically got regular fluid equations, one extra equation for the magnetic field evolution. There's various levels of approximation. So all of this is called non-ideal MHD. Okay, so this is ideal MHD. It's just like, let's take this term and ignore the rest. And of course, the universe is non-ideal. But the main thing where you care, so why would sigma be infinity? Well, that's saying, well, you're 100% charged. So you're 100% ionized, for example. Ideal MHD is a pretty good approximation. But if you have any level of partial ionization, which you always have somewhere, so for example, in star formation, it's a really big deal to think about the Hall effect and the ambient polar diffusion. They have different parameter dependencies. So for example, the Hall effect depends pretty strongly on the B field strength. If you think about what the coefficient is out the front of these terms in a sort of same dimensional way. So if you get low density material with strong magnetic fields, you tend to get the Hall effect. Ambient polar diffusion is kind of just low density material in general. Ambient polar diffusion kicks in, and resistivity kind of operates in the sort of high density, but all still partially ionized regions. So like in star formation, for example, you sort of think about ambient polar diffusion is sort of at the cloud scale. Hall effect is sort of at the star forming core kind of stage. And the resistivity is like when you're starting to like launch jets and do stuff very close to the star in the high density material. High density in like star formation terms.
Yeah, this is maybe not super important, but like Biermann term, that PE has to be some tensor or?
Well, we didn't assume it was. I mean, I guess in general, of course, it's like what Shane did yesterday. You know, that electrons can probably do all sorts of funky things that don't behave like gases. So yeah, we've assumed a scalar pressure here by writing the equations down. But
if it's scalar, then the del cross del would be 0, right?
Well, you've got an E and E stuff in the bottom still, so yeah. Okay, so that's deriving MHD. Now, what about solving MHD in the computer? Okay, so let's just talk about a couple of things which we don't really have time for. But so they're presented with a set of equations which are slightly different to usual. What would you do normally? Well, I'll summarize this with sort of differences to hydro. Or another way to think about the ideal, well, the non-ideal terms is these are kind of dissipative terms, right? So the things that destroy the magnetic field. So, well, except for the Hall effect, which is not. So it turns out this one's actually a dispersive term in the sense that it takes waves. Well, let's explain exactly what we mean by that. So let's talk about differences to hydro. Well, so hydro, what do you do? So you take rho equals rho naught plus delta rho, V equals delta V, delta P, P equals, delta P is sound speed squared, delta rho, you know, P equals P naught plus delta rho. You stick it in your set of equations, you say delta rho is some Fourier mode, e to the I k dot x minus omega t. So you put your perturbations in your equations, you drop second order terms, you wash it all out and you wash it through with this expression. What do you get? You get a dispersion relation that tells you that that's true in hydro. Okay, what does this tell you? Hands up if this is well, you don't have to admit that it's unfamiliar to you. Have you seen this before? Hands up if you have seen this before. Okay, so we're pretty good on the whole. Yeah, so what this tells you is that the hydro equations give you a solution which is basically traveling waves. Those waves are sound waves, as in there's two solutions here because it's a quadratic. So the two solutions are omega equals plus or minus CSK. And so those two solutions are basically a propagating wave that just simply shifts in time. So you get a kx minus omega t. So it's like saying I've got a kx plus or minus CST with this solution. So my solution to the hydro equations, the limit of small perturbations is propagating waves that I've got a wave traveling left and a wave traveling right. And you've seen that in the shock solution to the hydro equations. So for example, when you do the hydro equations, we think about characteristics. So what are characteristics? they're a nonlinear thing, but they're basically based on the fact we have a hyperbolic equation. We've got a single wave speed. So you get basically a wave. So this is time, this is space. So disturbances propagate on these lines of constant, well, they're called characteristics. They're lines on which certain things are preserved. So they're called Riemann. Something that's constant on characteristics is called a Riemann invariant. Okay, and there's an extra one in the hydro equations, which is what? Which is the contact discontinuity. Don't forget about it. All right, and that one propagates with x plus vt. All right, so this should be v plus cs if we're moving. V plus cs, this is v minus cs, yeah. Okay, so what's different in MHD? Well, this gets a lot more complicated. So it's like an entire lecture's worth of derivation, which we won't go through. Do you really want me to write it out? Let's try. I'm not going to have space on the board. So V, what's V here? V is the amplitude. So if I say delta V is some V e to the I kx minus omega t. So I've got the velocity of my, the amplitude of my velocity perturbation. Then I get something like this. So I get sound speed squared plus a b squared over mu naught rho v dot k. Okay. All right, so already there's something in this first term which we should look at and think about. We've got an extra term which has the dimensions of speed. So what's this? So I'm going to call it VA. Let's define it. So there's a thing that pops out that involves the magnetic field that has the dimensions of speed. It's the alpha in speed. Yeah, so if you do nothing else after this school, you should read the Alphane paper from 1953. It's like half a column and then like half of another column, where he basically just gives a short dispersion relation, says there's this new kind of wave, and he works out like basically the period should be about 5 minutes in the sun. Nobel Prize. Yeah, it's the most glorious piece of scientific writing you've ever seen. I challenge you to write a paper like that. Okay, but then you get like a big mess. So you get a b naught dot k squared over mu naught rho. So all right, so we're learning something here that we've basically got a new kind of wave. So cs squared k. I mean, the details are not super important here, but I just want to show you that there's a bit of a mess. V dot k. I'm running off the board already. B naught dot k. B naught. B naught is the background magnetic field around which I've perturbed my magnetic field, just like this. Okay, so you got some giant messy dispersion relation, which you have to solve, and there's an omega squared here, so it's actually a quartic already, this thing. But there's two kinds of waves. So, well, there's two kinds of solutions. Let's not say two kinds of waves, there's actually three kinds of waves. So there's V dot K equals 0. So what does that do? That knocks out that term, and that term. And if V dot K is 0, so that's like, what is V dot K here? If I take velocity equals this thing, then V dot K is like taking a divergence of V. Yeah, so if I say V dot K is 0, so that's a wave which does not involve any kind of compression or rarefaction of the fluid. Okay, and if I get that so that you can pretty much see that just gives me a V equals stuff involving V. So it gives you an omega squared equals, well, B naught dot K squared over mu naught rho. V. Well, that's what V's already cancelled out from both sides. V appears on both sides. So in other words, omega squared is VA squared cos squared theta K squared. So replacing my sound speed in the hydro equations, I've got something that depends on direction. So it depends on this cos theta, so the dot product between the B field and the wave direction. So these are called alphane waves. So they're not dissipative. What are they physically? Do we have any kind of long wiry thing? Has anyone got a cable? Oh, yeah, I see a cable. Yeah, here we go. Yeah, if you can hold the other end. It's great. I mean, this is your magnetic field. What's an alphane wave? It's that. Yep, so it's a transverse wave. Travels, sorry, shouldn't do that. Yeah, travels perpendicular to the field line. So thank you, great demonstration. It's just a wave that oscillates transverse to the field line. It's a new kind of wave that didn't exist in hydro. Okay, so that's one thing. So obviously the second batch of solutions, if we dot this with K and wash it all out, then you're going to get another kind of very long expression. And if we take V dot K, so I have given you a set of printed notes which has all of this in it. So if you want to follow it in a not done very quickly on the blackboard. But essentially then you end up with this expression after a little bit of algebra, but it's just algebra. So you get sound speed squared plus alphane speed squared plus or minus the square root of some other messy expression, sound speed squared plus alphane speed squared minus 4CS squared the alphane speed squared cos theta. So this is the same definition of this angle that we just defined. So B naught dot K, I'm just saying is like abs of B, abs of K, cos theta. Okay, so what is this telling me? Well, so this is basically what used to be my sound waves have now split. So the plus gives me the fast magnetosonic waves. So they're the sound waves, but they're modified by the magnetic field. And the minus gives me a slow magnetosonic wave. Okay, so what's happened to my very simple hydro with two waves going in each direction is I've got a new kind of wave, the alphane wave, and my sound wave is split into two things. It's split into a fast wave and a slow wave, sometimes called the fast magnetosonic wave, as in it's the thing that involves compression, as in V dot K is not zero. So these are things which involve squashing and stretching. So it's the longitudinal part of the wave. Yep, so the alphane wave is a purely transverse wave. It goes transverse to the field lines and it doesn't involve any compression. Whereas longitudinal wave is like how I'm speaking to you. Yeah, I'm compressing the air. It's bouncing along to you. Comfortable with that? Okay, well, predict for me what your shock will look like. No, so remember, so Andrew drew a really nice version of this. So, if you think about your shock structure, right? So if you think about your sort of SOD shock tube problem, for example, the characteristic here, so you got the contact discontinuity. So you can think about, so that's the contact. So the contact's non-compressive actually. So think about the way the density jumps. So let's do pressure jump. I'm screwing this up already. And you want you basically jump on the characteristics. What am I doing? This looked nice the other day. Also, the contact is where the fluids are in contact, something like that. Okay, so what's changing? So this was the sound wave going in one direction, the sound wave going the other direction. I had the contact where the fluids are in contact. What's new in MHD? How many waves do I have going in each direction? Well, so I'll tell you one more piece of information which you can work out. So V slow is less than V alphane, which is less than V fast. So that's always true. So how many waves am I going to have in each direction? So Andrew was talking about the Riemann problem. So remember we got contact. Let's do the fast wave. Yeah, fast wave is going to be the fastest thing. What else do we have? Alphane wave, it's going to be in between the fast wave and the slow wave. We've got the slow wave, yeah. And we still got the contact. Okay, so what's your shock going to look like? We're going to do this afternoon. How many discontinuities are you going to have altogether? Like 7, yeah. So you have all kinds of jumps which are not shocks, right? So you can have a fast shock, a slow shock. You can have something like what's an alphane shock? I mean, alphane shock is going to be not compressive. What is that? It's called a rotational discontinuity. It's basically a place where the field jumps and like the pressure doesn't jump. Yep, so you can have a discontinuity in the magnetic field that's not a hydro discontinuity. Yeah, so I've got new kinds of discontinuity. So the wave structure is just also reflected in the shock solution to my problems as well. I mean, they're just in order, right? So there's fast, slow, alphane, slow. This is the contact. Well, this is just the V star, basically. This is the V slow, this is the V alphane, this is the V fast. Yep, so for example, so it's interesting if you're studying like the outer parts of the solar system. So for example, Voyager is just traveling through the sort of shock structure of the sun's bubble hitting the interstellar medium. So it's passing through all these like funky regions where you're getting these like, you know, the various shocks going on from the banging into the interstellar medium. And so, for example, one thing they monitor is just the field, like when the field like flips direction. And Voyager went through the termination shock and various things like flipped, which is really nice. Okay, so there's one like real thorny issue that we haven't covered. So that's the basic, what changes in your physics. It's still like, well, actually, so it's still a hyperbolic set of equations. There's been some discussion on that over the years as well about how like strongly hyperbolic you should be. But essentially, like you can imagine your Riemann problem. So Andrew talked about all the possible, like you have rarefaction, shock, shock. There's like 4 possible combinations. You can think about all the possible combinations you could imagine when you got 3 waves traveling in each direction. Okay, so the first thing you have to worry about numerically is obviously if you want to solve your Riemann problem, it's a hell of a lot more complicated. And so people usually don't use the exact Riemann problem solution in MHD because it's a horrendous giant mess. So so people have done it. So there are exact Riemann solvers for MHD these days. And people do use them, but much more, usually people use these kind of approximate Riemann solvers. So the things you heard about like the HLL scheme, the only thing you need to know is the maximum signal speed, for example, or the signal speed of the main characteristics. So all you need to know is that fast wave speed, you replace your sound speed with that, and your job's basically done. So, so the complexity of the MHD equations is why you tend to go with these sort of more simple HLL type Riemann solvers. Okay, so let's just fast forward to the biggest issue of all. Okay, so what else? So we got this stuff. Okay, so we got an expression for E in terms of a bunch of other things. What happened to the other Maxwell's equations? We don't need the E. We've got our expression for E, so we don't need to evolve E in time. So we've kind of made an assumption there, which is kind of our assumption of neglecting the electron inertia, that the time dependence in the E field is not that important for the problems we're hoping to study. What about this one? Where'd that come in?
Isn't it already like the dot product of that equation?
I didn't do anything. I didn't make any statement about div B. Okay, so, but what she said to do is exactly the right thing. So let's take the dot product of this equation. So take div of 1, which is 1. What do we get? ddt of div B equals divergence of a curl is 0. So in other words, it enters the MHD equations as an initial value problem. That is, if div B is 0 initially, then it should be preserved for all time. Is it going to be true in the code? Absolutely not, right? So there's no way that any code can preserve this unless you are clever about what you do. So, so the whole knack to numerical MHD, and so okay, so why is this important? Let's discuss. So this is not the only place where this is an issue. So there's first of all, am I respecting Maxwell's equations? That's the sort of physics principle. But like, so what? You could ask. Why don't I just screw Maxwell's equations? Who cares? Okay, so one issue already. Let's just talk about this one. So let's do ideal MHD. So curl of V cross B. Sorry, curl of V cross B. Okay, let's expand this out. What is it? So it's a minus B div V plus B dot grad V minus V div V plus V dot grad. I want a minus there. I want a minus there. Oh yeah, because it's a curl. Yeah, so it must flip sign here. Yeah. All right, so I expand out my vector identity. What do I find? I find I got a term involving div B in here. Okay, what should I do? Should I use the curl of V cross B or should I use something different? I don't know. I mean, it should be 0, but it's not going to be 0 in my code, right? If I discretize the curl of V cross B, it's going to be slightly different to discretizing. For example, if I collect this term, and this term, well, so if I collect that term onto the left-hand side, so this gives, like in Lagrangian form, for example, this gives dB dt equals minus B div V plus B dot grad V. Do I want to add an extra V div B term here on my right-hand side? So it looks like, you know, in a Eulerian scheme, it looks like you would want to include it because it's inside. You just want to take a curl of V cross B. But in a Lagrangian scheme, I want to write dB dt Lagrangian derivative equals stuff. Do I want this thing here? No idea. No idea. What should I do? What if it was here? Okay, so let's consider dB dt equals the curl of V cross B. And let's do it in a, like, it looks weird if I write it in the Eulerian way, but if I write it with a Lagrangian scheme, this is a totally natural thing to do, is to say I want a minus V div B. In other words, I want to not include this term in the right-hand side. Okay, what do I get? So this is, let's call this number 2. Take the divergence of 2. What do we get? Well, I get ddt of div B I'm going to move it onto the left-hand side, plus divergence of V div B equals 0. Okay. So it's different. So I don't get 0, but what does this remind you of? So what it reminds you of is if you had monopoles in nature. So remember, so let's call Dirac. So Dirac played around with this stuff. So if you had monopoles in nature, you would say, well, I've got charge density, right? So limit with an epsilon. So div of B would be what? Would be like a magnetic charge density. So then this would basically be d rho m dt plus divergence of rho m v equals 0. So it's saying that if I had monopoles, let's pretend I had monopoles, then the right thing to do would be to, they would obey conservation law. And what's the conservation law here? So it would be integral rho m dv would be a constant, like mass. And what is that thing? So that is the integral of div b dv, which is, so this conserves the integral of div b dv, which is equal to the surface integral over delta v of b dot ds. So it's like the total flux. Yeah, so it's like a statement that like, so this might be, you can see why this might be already helpful, because this is sort of saying, well, let's just hope for the best. This is sort of saying, well, assume things are going a little bit wrong. Yeah, at least if things are going wrong, I'm going to obey a conservation law. And the conservation law is like conservation of like total magnetic flux through a surface, even if I have div B in my simulation. Right, so thinking about like what if you had div B in practice is already helpful here. So this is, so this basic idea of including this extra term. So this is sometimes called the Powell like 8-wave scheme. So they do a little bit more than that, so you can sort of put that into your Riemann solver. But so basically it's paying attention to what the extra div B terms do or do not do. Yeah, and thinking about just trying to do them in a self-consistent way. It doesn't really help you that much. It helps you like not completely cock it up, but like div B could still be a large number, right? It's just that on average, I'm going to have like the integral of div B dv is 0. I could have like +1, -1, but great on average it's 0. Yep, so it's not a real great scheme in practice, but it's better than that one. Yeah, in terms of like preserving. So there's a real simple test problem, which again we could do. So you just put some div B in your box and you say, what happens to it if I don't do anything clever? And the answer is, well, in this scheme, it will just be advected. So it'll just be preserved by the flow. And that's kind of a nice property. It's not enough. All right, there's another issue. So when we write our MHD equations, well, let's do it in Eulerian form. So d dt of rho v plus, we want like a nice divergence of stuff. So what's the divergence of stuff? It's rho vv plus pi. But what's the J cross B force give us? It gives us something which we can write, and you've seen this already several times on people's slides. It's like you want basically the divergence of a stress tensor. So it's turns into P plus a half B squared over mu naught, identity matrix minus BB over mu naught equals 0. So I can wrap the J cross B term into my conservative form of the MHD equations. But if you wash all that out, this gives me something which is already different. So if you expand all that out with your vector identities, gives me a J cross B over rho plus B div B over mu naught rho. So it's the same issue in the MHD equation, right? I've got a term which, if you do it in conservative form, you're sort of saying, I want this term to be there. But if you did it, say, if you just wrote down the way we derived our equations, this term was like not there. Yep, so the question is like, what would you do in nature? Would monopoles conserve momentum or not? If I had real monopoles in nature, would I still get momentum conservation? I would obviously get an extra force. So this is like a force that's directed along the field lines. So what's the right answer? So you think this is a small issue, but for example, in MHD and SVH, if we include this term, it's a complete and total disaster. As in, this term actually leads, well, in the regime where the magnetic field is strong. So if in the regime where the magnetic pressure exceeds the gas pressure, this term will actually give you an attractive force between particles, and it will produce like numerical instability very quickly. So in SVH, for example, we basically explicitly subtract this term. We try to control, well, so you want to make it small so it doesn't matter. That's the important thing, but even 10 to the minus 5 is still something you should think about. But obviously, if I want to write down my conservative Eulerian scheme, I want to include this term, right? As in I want to write it down in conservative form, right? But again, you could think about, well, what they would call it is a source term on the right-hand side. So it would appear as an extra term on the right-hand side over here, which would be like a B div B term. So you can think about, you know, should I include it? Should I not? So this is, again, in the power scheme, they do include it on the right-hand side. Well, actually, no, they don't include it, I think. But if you ask what real monopoles would do, real monopoles would actually conserve momentum. But this is just one of the little, so this is before we've even talked about controlling the div B errors. You've got to worry about how you formulate your equations, right? So this is a giant mess already. Okay, comfortable with this? All right, so how do we do better than this? Well, the answer is like, you'd like this thing to just be 0. But what does it even mean to be 0? So what does this even mean? So let's define the problem. So for example, let's say I'm doing finite differences. I could define div B, one dimension, as bi plus 1 minus bi over delta x. Is that the thing I want to be 0? But what if I did like a centered difference? So I could maybe make div B 0 in this discretization, but it wouldn't necessarily be 0 in this one. So you have to worry about not only, so even if you do like some kind of fancy scheme, even constrained transport, you're making div B 0 in some representation, but you still have to worry about the other ways you're representing it in your discretization. Yep.
Does it help go numerically to write B as the curl of the vector potential?
Yes, it does. So more specifically, so when you're doing, so the schemes that I'm not going to talk about too much because I'm not the expert, but you can ask Shane. So if you do constrained transport, it's not quite using the vector potential. Actually, I will discuss the vector potential briefly. It's the way you do this curl can be done in such a way that it represents like a vector potential on the cell faces. So this is basically the basis of the constrained transport method, is you kind of reconstruct what the vector potential is in the cell, and then you take your curl staggered between the cell center and the mesh. So you define the E field basically on the edges of the cell, on the cell faces, and then you take the curl at the cell center based on the cell faces. And that does kind of involve the vector potential. It's kind of implied in the way you write it, that you're using the vector potential to construct a divergence-free operator. Does that make any sense? Sort of. Okay, so, I mean, should I just use the vector potential? Well, it's a good question. So if you uncurl, what I mean by uncurling my induction equation, I mean integrating. So if I integrate the induction equation, I get B cross the curl of A. I get equals V cross B, which is V cross the curl of A. So the question is like, when you evolve the vector potential, you've got some freedom, right, which is called a gauge. And what's the typical gauge that you might want to use? So, I mean, this is a successful approach in the pencil code, but the typical gauge might be div A is 0. Yeah, how do I enforce that? I've just shifted the problem like one level higher. And Vlad said, well, we don't care, like essentially as long as it doesn't affect your solution. So they do this in pencil and it works okay. In Lagrangian schemes, vector potential is a disaster. You can ask me why I wasted a year if you really want. The paper on archive that I wrote on the vector potential is called 25 Pages of Pain. Don't try this at home. You can read it if you like. Okay, but there's a very simple way to like clean up the magnetic field that kind of works in any scheme. All right, so the scheme is basically, let's just add an extra variable. So this is called divergence cleaning. And it's due to Dedner. So they were mathematicians, which leads to some problems. They don't know about dimensionality, for example, of things. Okay, so what would you do with this thing? So one simple answer would you could just say, well, eta div b. And that just gives you basically a dissipative term that's proportional to the magnetic field. So this is like a parabolic term. So this is called parabolic cleaning. So it's like the heat equation. What do I mean by that? I mean that d dt of div b. So if I take the divergence of this equation, I would get eta del squared div b. And so that's like the heat equation. Yeah. So the heat equation would be one way, like, and that, you know what the heat equation does? It just like diffuses things away. Problem with the heat equation is if you do parabolic terms in your hydro equations, you end up with a time step constraint that goes like delta x squared over eta. And I'd really like eta to be infinity here. Yeah. And so when you start setting eta to like a large number, so for example, Shane was talking about flux limited diffusion yesterday. This is what you try to do when you make like a diffusion approximation. You're saying, well, I'm assuming that my propagation speed is actually fairly small. And when it gets high, what should happen, the radiation should start, instead of diffusing slowly, it should start to stream. And when it starts to stream, it streams like a wave, yeah, which travels at a wave speed. Okay, so hyperbolic cleaning is just exactly that. So you take d psi dt equals some speed. What speed could I choose? Well, there's some sensible speeds to choose in the problem. We've got the fast wave speed, for example. So let's add another equation here that tells me how my extra field, which is some random scalar we just invented, it's like a gauge condition or something like that. But it's just a numerical trick to kind of propagate my errors in a good way. So what do I get with this? So what you find, we can do it actually. So if we take the divergence of this thing, so d dt of div b, what do I get? It's del squared psi. Let's take d dt of this. So I get del squared psi dt squared equals minus ch squared d dt of div b. So already you can see that this gives us, you can write it in terms of, so it's simple if we write it in terms of psi. It gives us basically 1 over this speed squared, d squared psi dt squared minus div b, minus del squared psi equals 0. So we've got a wave equation. Now the good thing about waves is we know what the time step constraint on waves goes like. So I'm going to need a delta t is just less than like delta x or smoothing length or whatever you've got, divided by the wave speed. So what it makes sense to do is to choose the wave speed of like the maximum one that I'm already using in my problem. So for example, for MHD, that would be the fast wave speed. But if you could jack this speed up to infinity, you just have to take a smaller time step. Go on.
The last equation.
The last equation was just me taking the divergence of this equation. So I did div of this. which gives me a ddt of div b. This term goes to 0. This is a del squared, this is a minus del squared psi. Yep. Okay, and you can also show, I mean, it's the same equation for ddt, d squared, dt squared of div b actually obeys the same equation. Now, what I want to do is add an extra term. So this is just propagation, actually. It's not damping at the moment. So this one gives me del squared div b. So you can work it out, but it gives you the same equation for the propagation of div b. Okay, but what I'd really like to do is just not propagate it like a wave with no change in amplitude. I'd like to damp it. Okay, so then add damping. So damping is basically a parabolic term. So you instead of taking d psi dt equals minus ch squared div b, I then just on dimensional grounds, you can see that if I add a term like that, that's going to be e to the minus t of that is the solution to that part of the PDE, of the ODE. Yep, so I get psi equals, if I just had that term, my solution would be psi naught e to the minus psi over tau. Psi over tau t minus t naught. Yep, it's just a separable differential equation, so that's like d log. Everyone happy with that one? Okay, so this is basically called hyperbolic parabolic cleaning. Does it work? How long we got left? We're nearly there.
Minus some number
Oh,
of
minus
minutes.
one. Okay. So one key thing. So divergence cleaning has a bad reputation because you have some physics that's extra, which we haven't talked about. So you've introduced a new field. So I'm moving what was magnetic energy into a new field. So I have E. This is not the electric field now. This is a scalar energy. And it was half rho v squared plus rho u plus a half b squared over mu naught. But if I have a new field, then I should have a new energy. So I have an energy associated with this field. And you can derive this energy. It's like ch squared rho. Actually, no rho, if I write it like that. So let's call this E dash. And you must ensure, so if you want divergence cleaning to not go wrong, then you must ensure that basically if you did the pure hyperbolic business, so without the damping, you need to make sure in your scheme that you conserve energy. And if you don't do that, divergence cleaning can go very horribly wrong. But if you do that, basically you guarantee that any energy you remove from the field sticks around. And basically when you add damping, it only goes negative, like it goes one way down. So you don't want two-way divergence cleaning. You don't want to get energy from the universe. You just want to pour some of this into this and then kill it. And so there's various ways of doing this. So in SPH, it's just to do with the choice of operation, the choice of operators that you use when you measure div B. So when you have this term in your equation, it's the choice of operator you use here, and it's the choice of operator you use in the grad psi equation. But in a finite volume scheme, it's you would formulate it slightly differently. You basically redefine your energy to include this term. You write things in an energy conserving way. And if you do that, divergence cleaning is not always guaranteed to be enough, but it's guaranteed to not go wrong. Yeah, and then, well, the question about is it not enough, you can always jack this speed up arbitrarily to give as much cleaning as you want, basically for your problem that you're interested in. So you just have to pay for it. So free cleaning is like take the maximum speed in the problem, and not free cleaning is jack the speed up to whatever you need to get things under control. Yeah, and this actually works great. So once we did this kind of scheme, which was 2012, so this business about conserving energy, you have to ensure that this E dash is conserved. So we did this in like 2012 in the context of SPH. But the principle is not specific to SPH, and there's also a 2016 paper where we accounted for the fact that often you want this cleaning speed to be variable. So you want it to go up and down and change low, be individual to the local. And you want to make sure that you conserve energy even when that's true. And you can work that out. Essentially what you do is you take ddt of psi over ch as your variable instead of taking psi as your variable. Well, it's like ch div v. That's the basic gist of it. That's basically it. One other thing on divergence cleaning is that this is like what we do for the MHD equations. You have exactly the same principle in numerical relativity, and they couch it in different language. So they have what they call elliptic constraints. What's an elliptic constraint? It's like div b equals 0. It's an elliptic equation. And you want to ensure that in numerical relativity, it's called the momentum constraint and the Hamiltonian constraint. And what do they do? So they're formulations of that. So for example, there's a ZZC4 formulation of numerical relativity. And basically they write out their equations in exactly this way. So they get hyperbolic propagation of the constraint violations. And exactly the same thing, they do a hyperbolic propagation with a damping that then kills any sort of numerically generated constraint violations that they take place. So it's exactly the same principle. In fact, those guys invented it first, and they're using it quite happily for doing numerical relativity accurately. So this is just a simple version of that for MHD. And so, for example, doing MHD and Lagrangian schemes, this is the key thing to get right, is getting your divergence errors under control. Coffee time.